So we'll continue on with Chapter 8 with hypothesis testing. In 8.2, we're going to review and build off what we learned in 8.1. So we'll go through another full example using hypothesis testing for testing a claim about a proportion specifically. These are the only two sections we're covering in Chapter 8, so 8.1 and 8.2. You don't need to worry about anything else in Chapter 8 aside from what we cover in 8.1 and 8.2. Our coverage of 8.2 will also most likely help solidify concepts that we went over in 8.1. So the key concepts in 8.2, the first is that we'll go through the complete procedure for testing a claim made about a population proportion. Another reminder here is that our population proportion is represented by lowercase p. Remember that parameters describe a population, whereas statistics describe a sample. So for the category of proportions, a population proportion is lowercase p, whereas a sample proportion is denoted by p hat. So I mentioned we build off 8.1. So in 8.2, within this category of a population proportion p, we will illustrate hypothesis testing using the p-value method, the critical value method. So within the topic of hypothesis testing, we have the category of proportions, means, and standard deviations / variances. In 8.2, we're only covering that first category, so within proportions. So within 8.2, we can use methods in this section for claims about population proportions, also probabilities, and also the decimal equivalence of percentages. As you look at each of these three here in this list, you'll see that they're all somewhat similar. Or we could say the proportion of a population is similar to the probability of a population, which is similar to the decimal equivalent of a percentage. For example, 60% of the population, that's the same thing as saying 0.6 probability. That's also the same thing as saying a 0.6 proportion of that population. So again, in 8.2, we're applying these methods to population proportions, but also keep in mind we can apply these methods to probabilities and decimal equivalents of percentages. To continue on with more key concepts in 8.2, so there's different methods for testing a claim about a population proportion. We're going to go through all these methods in 8.2. In part of this section, we're going to use a normal approximation to a binomial distribution. Then, aside from using a normal approximation to a binomial distribution, in order to test claims about a population proportion, we'll also go into other methods we can use to do this that might require the use of technology like Excel. Let's go through this method now. So testing a claim about a population proportion using a normal approximation method. The underlying objective in using this method is still to conduct a formal hypothesis test of a claim about a population proportion P. So this is our objective, but here we're going to apply the normal approximation method. Let's go through some notation now. So lowercase n is still our sample size or the number of trials. Lowercase p, it's what we've seen, it's our population proportion. We'll review this again in 8.2, but we saw in 8.1 that p is the value used in the statement of the null hypothesis. We'll go through those steps again from 8.1 in 8.2. And p hat is our sample proportion. We know how to calculate that intuitively. We can also use this equation to calculate our sample proportion, where x is sort of the number of successes we're interested in out of our entire population, or n. If, for example, we had a sample size of 100 and we were interested in the p hat, or the sample proportion of 30 individuals out of 100, then we would take 30 out of 100 to get our p hat value. So we can represent p hat by this fraction and also in a decimal form. You may remember from 8.1, it's more accurate to use a p hat value in the full fraction form that's unrounded, rather than using a p hat value that's in its rounded decimal form. We'll see that again today in 8.2 as a refresher. Then our notation for Q that we've seen before as well. To find Q, that's the complement of P. So we take Q is equal to 1 minus P to get our Q value. Okay, so we're still on this topic of testing a claim about a population proportion, and this method we're going through right now is using a normal approximation. In order to use this method, we have to check off these requirements. The first is that the sample observations are a simple random sample. They're not from a biased sample, for example. Number two, because we're using a normal approximation to a binomial distribution, we also have to check off the conditions for a binomial distribution. We've seen these requirements previously in our course. Let's cover them again here. So there's a fixed number of trials. The trials are independent of one another. So for example, the outcome of the first trial would not impact the outcome of 100 trials later. Then, because we're working with a binomial distribution, bi meaning 2, so each trial has 2 categories, either a success or a failure. So remember, for binomial distributions, we have to categorize our data as either a success or a failure and no other option. Then this fourth requirement of a binomial distribution, the probability of a success remains the same in every trial. Then again, if the probability is 0.1 for the first trial, then the probability remains the same, so 0.1 for 100 trials later. Okay, so this was our first requirement. This is our second requirement. We're lumping all of these in together to the requirement of a binomial distribution. The third requirement now should look familiar. So the conditions of n times p has to be greater than or equal to 5. And also n times q has to be greater than or equal to 5. Then going back some ways in 6.6 is where we originally covered this. The population mean for a binomial distribution we estimate as n times p. And the population standard deviation, or sigma, we estimate as the square root of n times p times q. One important thing to note here as we connect a binomial distribution to hypothesis testing is that the p used here in these equations is the same one as the assumed proportion used in the claim for our hypothesis test. So we get this p-value here to put into estimating the mean and the standard deviation from our original claim. This is instead of seeing p here in these equations and choosing to use the p-hat value. So we're not going to use the p-hat value here. We're going to use the p-value from the assumed proportion that's in the claim for our hypothesis test. Let's continue talking now about this topic of using the normal approximation here to test a claim about a population proportion. Going back to 8.1, this idea of a test statistic should sound familiar. So to calculate a test statistic for testing a claim specifically about a proportion, then remember we calculate the z value here. We do so by taking p hat minus p all over the square root of p times q over n. If you recall from 8.1, different test statistics would be calculated if we were working with a proportion, a mean, or a standard deviation / variance. In 8.2, we're only working with proportions, so the test statistic we need to calculate is this z value here. Then again, going back to 8.1, we can calculate a p-value. We can also calculate a critical value. In 8.2, we will go over again how do we calculate a p-value and how do we calculate this critical value. So you saw this initially in 8.1, but we'll go over this again today. Let's use an example that should sound very familiar to what we saw in 8.1. So here our claim is that most consumers are uncomfortable with drone deliveries. This is almost the same exact example we saw in 8.1, but here in 8.2, notice this word of most rather than a majority. But you'll see as we go through this, all the similarities between majority and most as a claim. So here's some numbers to work with. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases. 54% of this sample, or in numbers, would be 545 out of 1,009. That number of consumers responded with, no, I would not be comfortable having a drone deliver my purchase. So we're going to use this setup now to test the claim that most consumers are uncomfortable with drone deliveries. You saw in 8.1 how we interpreted the word majority. Now in 8.2, we still again interpret the word most to really mean more than half. Or in terms of P, we have a value that's greater than 0.5. Okay, so here's our setup, here's our claim. Now, in order to treat this like a normal approximation, we first need to check the requirements. After we check those requirements, we'll go through each step 1 through 8 to actually set this up like a hypothesis test. So again, we're testing a claim about a population proportion. One of the methods we're going to use to actually execute that is as a normal distribution. Then before we go through steps 1 through 8, let's check those normal approximation requirements. So to check these requirements, number 1, 1,009 consumers are randomly selected. One way these 1,009 consumers would not be randomly selected is, for example, if we were waiting outside of a drone convention and then we asked some of those people exiting the convention. Here we're not doing that, so we're assuming that the 1,009 consumers were selected randomly or selected in an unbiased fashion. Then requirement number 2 is checking off all of those binomial distribution requirements, so let's see how we do there. So we do have a fixed number of trials. We have 1,009 people that we surveyed. We're not adding any people to our survey. We're not taking any away. So we have a fixed number of trials. These trials are independent of one another because we could ask the first person and then their response doesn't impact 100 or 1,000 people later. Also for a binomial distribution, remember we have to have 2 categories. So here we do. Either the subject is uncomfortable with drone delivery or they're not. They are comfortable with drone delivery. So those are 2 categories that make up this binomial distribution. Let's check the third requirement now. So n is equal to 1,009, p is equal to 0.5. We got this value of p from our original claim of most consumers. If our original claim was 3/4 of consumers or some other number like that instead, then our p-value would be 0.75. Here, our claim is for most consumers, so we split that up into 0.5 that are uncomfortable, and then the other 0.5 would be the ones that are comfortable with drone deliveries. So again, our claim, most consumers, then P is equal to 0.5. Then we solve for Q by taking 1 minus P. That's also equal to 0.5. With the claim of most consumers, we're really asking about a number more than 0.5 or a probability more than 0.5. So our p-value is 0.5, our q-value is 0.5. Now we can go on to check, is n times p greater than or equal to 5? And is n times q greater than or equal to 5? Well, n is 1,009, p is 0.5, so multiplying these together, we get 504.5. That is definitely greater than or equal to 5. Same thing here for n times q, because p and q are the same numbers, so n times q is also greater than or equal. Then we say from requirement number 3 that these requirements n times p is greater than or equal to 5, as well as n times q. Now from these steps, we can say that the requirement checks are satisfied. Remember that these requirement checks were particular to using a normal approximation to a binomial distribution. So now that we've checked all those requirements off, now we can proceed with the solution. These steps are what we went over in 8.1. Let's go through all of them again in detail. Step number 1 was to make our original claim into symbolic notation. Our original claim here is that most consumers are uncomfortable with drone deliveries. In symbolic notation here, that's a p-value or a population proportion value that is greater than 0.5. It's not going to be equal to 0.5 because we want to know if most consumers are uncomfortable with drone deliveries. So P is not going to equal 0.5 for our claim here. P has to be greater than 0.5. Step number 2 is to figure out the notation that's opposite to our original claim. If our original claim is that P can only be greater than 0.5, then the opposite of that is that P would be equal to 0.5 or P is any number less than 0.5. How we represent all of that symbolically is to say that P is less than or equal to 0.5. Okay, so that was step number 1, that was step number 2. Let's go on to step number 3. Step number 3 involves figuring out our null and our alternative hypotheses. Remember, the trick to solving for this is to figure out which of those notations from step 1 and 2 contains inequality and one that does not contain inequality. I went back to this slide here, so P is greater than 0.5, that's one of our options, and P is less than or equal to 0.5. So using what we just saw, P is greater than 0.5, that expression does not contain inequality. Therefore, this expression is our alternative hypothesis. Okay, so again, for an alternative hypothesis, we go back to steps 1 and 2, and we figure out the one that does not contain inequality. Then that one is our alternative hypothesis. Then recall how we think about the null hypothesis is a little bit different. So for our null hypothesis, it's always the statement that P equals the fixed value of whatever our claim relates to. So our null hypothesis here is that P is equal to our fixed value of interest. Again, we're working with a fixed value of 0.5 because we're interested in the idea of most consumers being uncomfortable with drone deliveries. The null hypothesis always contains an actual equal sign here. So then to sum all this up, our null hypothesis, or H0, is that P is equal to 0.5. Then for our alternative hypothesis, H1, is that P is greater than 0.5. Some checks to look at here is that our null hypothesis contains an equal sign. Our alternative hypothesis does not contain an equal sign. More specifically, it does not contain an equal sign in any form. So it's just P is greater than 0.5. We don't see a line under here to denote that it's greater than or equal to 0.5. P is just greater than 0.5 for our alternative hypothesis. One thing we'll end up doing is figuring out, is our original claim our null or our alternative hypothesis? Here we're already starting to connect this, so we know that our original claim is that P is greater than 0.5. Therefore, we see here that our original claim is, in fact, our alternative hypothesis. We'll use this later. We didn't necessarily have to say at this point in this step that our original claim is our alternative hypothesis, but it's good to know moving forward. Step 4 relates to our alpha significance value. So here we're going to use an alpha value of 0.05. Remember, there are a few other choices for alpha. Usually we'll be given one, or by default, we decide that alpha is equal to 0.05. So that was steps 1 through 4. Then, as you may recall, in step 5, we need to figure out what test statistic we need to calculate. Within this section 8.2, we're working with population proportions P and sample statistics, or P hat. Recall the same notation we've seen. A population proportion is equal to P, whereas the corresponding sample statistic or sample proportion is P hat. Now, thinking back to a second, what we saw in 6.3, we know that when working with a sampling distribution of sample proportions, or P hat values, these can all be approximated by a normal distribution. Now, what this looks like visually, if you remember from 6.3, is that our distribution of sample proportions, or P hat values, can be approximated as a normal distribution. Okay, so that's some background on why we're using a normal approximation for this method here in 8.2 when we're evaluating test claims about population proportions, where the corresponding sample statistic to a population proportion we know to be a p-hat value, which we also then remember that we can estimate a distribution of these p-hat values as a normal distribution. Now, showing this flowchart again, because we just got to this part in step 5 when we're about to identify the test statistic and then calculate that. I mentioned in 8.2 we go through the p-value method and the critical value method and also the confidence level method. As we proceed in 8.2, we're going to follow this path first and go down the p-value method. In both the p-value method and the critical value method, we're first going to need to calculate the test statistic that we identified in step 5. So let's do that now. So because we're working in the category of proportions, then we know the corresponding test statistic value we need to calculate is the z-value. We did this in 8.1 initially, so here's this equation again. Here's our equation for our z-value. To calculate the z-value and to calculate the z-value more accurately, let's figure out what all values we need to plug in here. The first is our p-hat value. Remember, we take our x value, or the number of interests, divided by the total number of consumers. The x value of interest in our original problem was asking about 545 consumers out of the 1,009. Now remember, to make this more accurate, we're going to use the full version of the fraction and not the decimal form. Next, our n value, that's 1,009, that's our sample size. Then p we figured out initially as well, that's p is equal to 0.5. We know this from the original claim being most. We also know this from our null hypothesis, which used the same reasoning. So our p-value is equal to 0.5. We want to know if most consumers are uncomfortable with drone deliveries. Not if 1/3, not if 3/4, not if 5/6, but if most. So this idea of most comes back to this reference point of half, where most is greater than half, right? So we come back to this p-value of 0.5. Next, we calculate our q value, where p and q are complements to one another, going back to our binomial distribution section, where p and q add up to 1, so q is equal to 1 minus p, or 1 minus 0.5, so q is also equal to 0.5. Now, before we plug in these numbers and calculate for our z test statistic, I wanted to go back to this table and show you why we're working with this row here in this table. You should remember seeing this table from 8.1. Remember, in 8.2, we're specifically working with proportions. So whenever we're working with proportions in 8.2, our corresponding test statistic is this z-value here, and we calculate it by this formula. So technically in step 5, we figured out that yes, we're working with a proportion. That means our test statistic is a z-value. Then in step 6, we proceed in calculating the z-value. Here's the setup that we know so far. We know our p-hat, our n, our p, and our q. We're going to use this formula and start plugging in what we know. Remember, we're going to be more accurate always when we can, so we're putting in the fraction form here of our p-hat value. So p-hat minus p all over the square root of p times q over n. Again, very importantly, I'm circling this because I'm not using my decimal form of p-hat. Instead, I'm using this full unrounded fraction. We're going to use a p-hat value as our fraction whenever we can, whenever that information is available to us and what goes into that fraction. If we're told a p-hat value in decimal form, then we can use that decimal form, but when it's available to us, we're going to use the full fraction for our p-hat value in calculating the test statistic. So we do this very carefully in our calculator or very carefully in Excel, and we should get a z-value here. Our test statistic of z is equal to 2.55. Now that we know the z-value of 2.55, we can either use table A2 or Excel, and we'll go through both methods now. If you're referring back to the textbook and you're on page 387 and you go to figure 8.1, that lists the steps for using the p-value method. We're going to use those methods here and use table A2. One thing to connect here is that because the hypothesis test is right-tailed with a test statistic of z is equal to 2.55, then our p-value method is the area to the right of z equal 2.55. Now, why is this considered a right-tailed test? Well, remember to figure that out, we can go back and look at the notation that's in our alternative hypothesis. Here's this image we've seen before for a right-tailed test. If you want to go back to 8.1, you can also see the images for a left-tailed test and a two-tailed test. To connect our original example to, is it a right-tailed test, is it left-tailed, is it two-tailed, we need to look back at the notation in our alternative hypothesis. For us, our alternative hypothesis has this notation of p is greater than 0.5. Then, because in our alternative hypothesis we have this greater than symbol, sort of points to the right, then we know that we're dealing with a right-tailed test. Then, because we're dealing with a right-tailed test, we're interested in the p-value, which is the area to the right of z equal to 2.55. But remember, for table A2 and using Excel, we're always making reference as far as area from the left, or cumulative area from the left. So for a right-tailed test, we're not going to get this area right away, but we can get this area from the left and then do 1 minus this area from the left to get our area here to the right, which is the p-value we're interested in here. Let's use table A2 to do this. Remembering that when we find a z-score in table A2, it's really giving us our cumulative area from the left. Then I'm showing you this more condensed version of table A2. So when you go and look at it in your book, there's going to be a lot of numbers in between here, between z and 2.4. In this display here, I just cut out all the middle points here because we're only interested in a z-score of 2.55. So for the steps here, we find 2.5, then we go over to the 100ths place of 0.05 because our value of interest is 2.55. We locate that probability or area value to be 0.9946. Remembering again that table A2 and Excel always tell us in reference of cumulative area from the left, so we know this value here is our cumulative area from the left using a z-value of 2.55. So we're one step further here, but really we want the area to the right of that z-score to get our p-value of interest for a right-tailed test. I put this definition again here from 8.1 to remind us what our p-value is and how we use this method. So remember that in a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic itself. So for us here in this example, our z-value is 2.55, then our p-value is getting a probability or area that's at least as extreme as that z-value. And at least as extreme for us is going to be any number that's to the right or that's greater than that test statistic or that z-value. So to truly get our value of interest then, to get the right of the test statistic, we take 1 minus this value, so 1 minus 0.9946. We did this in 8.1, but we actually got the same value here that we saw in 8.1. That makes sense though, right? Because in 8.1, we had the claim of majority, but here in 8.2, we have the claim of most. Majority and most actually lead to the same null and alternative hypotheses, so it makes sense here that we got the same p-value we saw in 8.1. So again, this was us using table A2 to get our p-value of 0.0054. So to visualize this now and getting our p-value of 0.0054, we can look at this normal distribution, this normal approximation. In terms of p-values or proportion values here, we are interested in the idea of most consumers, so we had a p-value of 0.5. Our corresponding p-hat value, our sample proportion, was 545 consumers out of 1,009. When we calculated our test statistic, our z-value, we were approximating our data as a normal distribution. From that test statistic calculation, we got a z-value of 2.55. Then our p-value is the area to the right of that because we're dealing with a right-tailed test. So then we found this area to the right to be equal to 0.0054. That's the p-value that we get, and we originally got that first by finding our test statistic, our z-value. Then we used table A2 to find the cumulative area from the left. Then we took 1 minus that cumulative area from the left to get our true p-value, or this area of interest. As a reminder here, we've still been in step 6. So now we're going to solve for the p-value method using Excel instead of table A2. As always, practice with both methods and figure out which one you're more comfortable with moving forward. Now we solved for the p-value using Excel in 8.1. This was on slide number 31, just for a connection and just for more of a review if you'd like. So here in 8.2, we're actually dealing with the same numbers, so let's go through this again. Now, what I'm not showing explicitly is that you can also calculate this test statistic, the z-value, in Excel. What you can do is set up different cells with all these values here, your p-hat value, your n value, p and q, and then plug all your numbers into a function that's set up like this, where you take p-hat, but in the fraction form, not the decimal form, minus p all over the square root of p times q divided by n. I prefer to use Excel for this because I find that I can catch little mistakes easier with Excel than I can with a calculator. Now, in both Excel and with your calculator, always remember to use parentheses in the correct place. Okay, so either calculating this with Excel or with a calculator, we still move forward with a z-value of 2.55. Now, coming back to this slide, I'll show you how I solve for my p-value using Excel. The key point here in solving for a p-value with Excel is to remember that we're really approximating this as a standard normal distribution where the mean is 0 and the standard deviation is 1. Now, aside from knowing the mean and the standard deviation that we associate with a standard normal distribution, I also need my z-value that I previously calculated either in Excel as well or with my calculator. Then this cumulative value is either 0 or 1. Here we're using a cumulative value of 1, right? Because I want a range of area, a range of probability values, not at some single value for x. Or in this case, with a standard normal distribution, not for some single value of z. Then the function in Excel we can use for this is our normal distribution function. For this function, we need our x value, we need our mean, standard deviation, and our cumulative value. Now, again, because we're working with a standard normal distribution approximation, we know our mean and we know our standard deviation values. Our x value of interest is now our z value that we found from calculating our test statistic, so that's 2.55. Then we know about our cumulative value already, so we click enter and we get a value of 0.994614. We remember that Excel and table A2 are always in reference for cumulative area from the left. So we know we're not quite done yet. We really need to take 1 minus the cumulative area from the left, where 1 is the total area under the curve. So to find our p-value, our area to the right of that z-value, we take 1 minus 0.994614. I set this up in Excel as well to take 1 minus the value here. When I click enter and I round off to the number of decimal places that I'm interested in, I get my same p-value of 0.0054. Now, we got this conclusion using table A2. We also get the same conclusion using Excel. So what we can say is for a right-tailed test with a test statistic of z equal to 2.55, we have a p-value of 0.0054. Recall again, that was still all in the step of step 6. So now let's move on to step 7 and 8 and make a conclusion. So remember for step 7, we need to compare our p-value to our alpha significance value. The two options when we do this is that we get a p-value that's less than or equal to our alpha value. If that is the case, then we reject the null hypothesis. Our other option is that our p-value is greater than our alpha value, then we would fail to reject the null hypothesis. Now for our example, we have a p-value of 0.0054. That's definitely less than or equal to our alpha value of 0.05. Putting that together, we would say that we can reject the null hypothesis. That's all we say from step 7 now. So we reject the null hypothesis. Now let's move on to step 8. So in step 8, we have some questions we can ask that will then help us look at the correct place in this table to then make the correct conclusion. To figure out where we're at in this table, the questions we can ask: do we reject or do we fail to reject the null hypothesis? Why is that one of the questions? Well, we can see here with the conditions, we either reject the null hypothesis or we fail to reject the null hypothesis. So when we answer this, we'll be closer to figuring out what conditions we're under. Then once we ask, does our original claim include inequality? Then we'll be able to narrow it down to just one of these conditions. Let's answer these questions now. So the first being, do we reject or do we fail to reject the null hypothesis? Well, what we just saw in step 7 is that our null hypothesis is p is equal to 0.5. And we decided in step 7 we would reject the null hypothesis. So we reject the null hypothesis. This also means we support the alternative hypothesis of p is greater than 0.5. Okay, so we've established these. The key takeaway in order to look at the right place on that table is knowing that we reject the null hypothesis. Let's go to our next question now. So does our original claim include inequality? Recall that our original claim is that most consumers are uncomfortable with drone deliveries. We expressed that claim in symbolic notation originally in step 1 to be p is greater than 0.5. So for this question, does our original claim include inequality? And to remind you again about how we denote equality with an equal sign or less than or equal to or greater than or equal to, it's apparent that our original claim does not contain inequality. Okay, so in step 8, we reject the null hypothesis and our original claim does not contain inequality. Now let's see where we fall on that table so we can word the proper conclusion. So for our example we've been going through, we end up falling in this first row, right? The original claim does not include inequality and we reject the null hypothesis. The corresponding conclusion for this is there is sufficient evidence to support the claim that, and we insert our original claim here. Let's do that for our example. So there is sufficient evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. That's really the same wording here. We conclude that there is sufficient sample evidence to support the claim that more than half or most or a majority of consumers are uncomfortable with drone deliveries. Okay, so in this first part of 8.2, we went through the p-value method for testing a claim about a population proportion. In the next part of 8.2, we're going to go through the critical value method. With that, I will see you shortly for 8.2 part 2. As always, let me know if you have any clarifying questions or any questions at all about any of the content. We're getting closer to the end of the semester now, so I hope you're all doing well and hanging in there. So I will see you next time.